Hi, I'm Rick Gillen. Welcome back to Coolerado. In this video, we will show you how we were able to achieve the 100 Fahrenheit temperature drop that you witnessed in the introduction video. We will also describe the basics of how we are able to cool below the wet bulb temperature of incoming air. Let's begin by taking a closer look at direct evaporative cooling, which is commonly referred to as swamp cooling. Swamp cooling has been around for thousands of years. You simply blow air over a wetted surface so that the air evaporates water off the surface and into the airstream. Common residential swamp coolers blow air through shredded aspen trees contained in a mesh and wetted by continuously pouring water from above. Commercial and some residential swamp coolers use a corrugated cardboard system instead of aspen trees, which works in a similar fashion. When water evaporates into air, it changes state from a liquid to a vapor, and it absorbs heat from the air surrounding it. The total energy within the air stays the same, but the air feels cooler because the water molecule has absorbed and hidden the heat within the air. Again, the total heat energy in the air stays the same. Air can only hold so much water. The temperature limitation for adding water to air is called the wet bulb temperature. Aspen pad swamp coolers can reach to about 70% of the wet bulb temperature from their starting point. Corrugated cardboard type swamp coolers are better at swamping the air, and they can reach to about 90% of the wet bulb temperature. These types of mechanisms are called direct evaporative coolers because they add moisture directly to the air that enters the building. Direct evaporative cooling is adiabatic cooling, which means no heat energy is removed from the airstream. The heat is simply hidden in the water molecule in the air. Indirect evaporative coolers use the principles of evaporation, but it does not add any moisture to the air entering the building. An indirect evaporative cooler utilizes a heat exchanger. A common example of a heat exchanger is the radiator in a car. The hot liquid in your car's radiator transfers heat to the air outside without the air from the outside getting in, or the hot liquid from the inside getting out. The same heat exchange principle is true for an indirect evaporative cooler. This is a plastic-coated piece of paper. It is paper on one side, coated with a thin layer of plastic on the other. If you wet one side of this paper with water and blow air past it, the water evaporates from the paper and cools the plastic. In this process, you are exchanging mass in the form of water to vapor in the air. The plastic is the heat exchanger, and it in turn will cool and pull heat away from the air on the other side. This is similar to how your body, skin, and perspiration work together to cool your body. Indirect evaporative cooling is called sensible cooling, and heat energy is removed from the product airstream. Now imagine mounting this plastic-coated paper in the middle of a long insulated tube, much longer than you have here. Then imagine wetting the paper side with water and blowing air through the tube. The air on the wet side is going to absorb moisture until it reaches the wet bulb temperature. That process will pull heat away from the plastic, which will in turn pull heat away from the adjacent airstream. When you come out the other end of this long imaginary tube, the air on the plastic side will be dry, and it will be close to the wet bulb temperature of the entering airstream. This is indirect evaporative cooling. It is both a heat and a mass exchange process. So in theory, the conditioned air you get at the end of this long pipe is going to be about half the quantity of the air you started with, and it will be cooled to the wet bulb temperature without adding any moisture. But we know that Coolerado coolers can cool below the wet bulb temperature, and our theoretical limitation is cooling towards the dew point temperature of air. Let's go back to your theoretical long tube heat and mass exchanger. When the air comes out of the dry side of the pipe, it will be cooler, and its wet bulb temperature will have been lowered. You'll throw away the humid air from the wet side to the atmosphere. Then you'll take the dry side airstream, and you'll run that down yet another one of your heat and mass exchange pipes. After throwing the humid air away again, you'll end up with 1/4 the amount of the air that you started with, and this air will be cooled below the original wet bulb temperature. If you keep repeating this process, you can theoretically approach the dew point temperature of the original airstream. However, you'd only end up with a small fraction of the quantity of air that you originally started with. In addition, you'd lose a bunch of energy to friction and pressure drop losses, so the process would be of little value. But Coolerado coolers have a small pressure drop loss, less than 1-inch column of water. We only throw away about 50% of the incoming airstream. And we can cool toward the dew point temperature of the incoming air. With this knowledge, you can begin to understand the pure genius of the Mises-Cinco cycle. Let's take a look at the Coolerado heat and mass exchangers that we use in our demonstration cooler. The plate heat exchangers are made from the same plastic-coated paper that I showed you earlier. We attach guides to these plates to create channels for air to flow through. We then assemble these plates together to create a heat and mass exchanger. All of the air being pushed by the fan enters this end of the heat and mass exchanger and begins to flow in this direction. The air that enters the top half of the channels travels straight through to the other end and only comes into contact with the plastic side of the heat exchanger along the way. When we look at the product end of the heat and mass exchanger, we can see that the lower half of the channels have been blocked. These channels are our working airstreams. The air that enters the lower half is the working airstream. All the working air initially enters the dry channels. Within the first inch, the first 1/13 of air is fractioned off and goes into an adjacent wet channel. The wet channel is wet because it is sitting in a reservoir of water at the bottom and wicks the water up along the length of the wet plate. The wet channel is perpendicular to the dry channel and exits out the top of the heat exchanger. As the first 1/13 of air travels in cross flow to both the working and product air, it takes heat away from the dry channels from the plastic heat exchanger. This same process occurs another 12 times, incrementally cooling both the product and working airstreams as the air travels down the heat and mass exchanger. This is the heart of the Mises-Cinco cycle, incrementally cooling both the product and working airstreams through heat exchange while incrementally fractioning off some air to aid in lower temperature vaporization and mass transfer. In short, this elegantly ingenious and simple process is how we achieve temperature drops that have never been seen before. This huge temperature drop is created with a little water and the power of a fan. In fact, if you could harness the wind through this little machine, you would not need any power at all. We invite you to view the next video titled Humidity in Coolerado Cooling. We'll examine what regions of the world and projects are a good fit for Coolerado coolers.